the circuit. Now, power due to work over time, work is equal to VI. Okay, we've already done that in this section already. So power is equal to VI over T. Oh, sorry, I got that wrong. Let me do that again. Recalling from section 118.1, work is equal to VIT. So work is VIT over T, which then, if I cancel my times out, what is work equal to, or power equal to? VI. Okay? Now I can do some substituting into this now. I can substitute my V, if I have R, let's say, okay, or I want resistance, so I've got VI here, right? So how do I find I using Ohm's law? That's V over R, correct? So I can go V times V over R, which is power can be calculated if I'm given the voltage and the resistance. Power can be calculated by taking V squared over R. So that's another one of the equations. Let's say that I don't have voltage, that I have I and R. So from Ohm's law, V is equal to IR, correct? So if I substitute IR in for V here, I end up with I squared R. So the long and short of it is this. Depending on what I'm given, depending on what I've been given in my circuit, I can calculate my power by taking VI. I can calculate power by going V squared over R if I'm given volts and resistance. And power is equal to I squared R if I'm given current and resistance. So depending, you're always going to be given 2 of the 3 pieces of information again. You can always find the other piece of information just using Ohm's law. Fair enough?
Yeah.
Okay, so this is not too much new to you. I'm going to look at an example here. Here's what we're leading up to. So we're using our circuits again. Okay? This particular circuit has an EMF of 3 volts. So what's the EMF on each individual battery? 1 volt. Has a total of 0.5 ohms internal resistance and a load resistance hooked up of 1 ohm. So doing the same thing that I did in the last section, but much easier, of course, because I don't have dynamic circuits hooked up. The only thing I'm going to add to this is power at the end of it. I want to find the power in the battery. I want to find the power with the internal resistance, and I want to find the power in the load resistance. So it looks like this. I'm going to go R, L, R, T, V, I, R, P. Load resistance.
Oh, okay.
Load resistance, if you remember, was outside the battery. So like a light bulb is hooked up. Right?
Yeah.
Okay, that was the very first thing that we did in that last unit. Okay, so I have this given to me as 3 volts. My internal resistance is 0.5 ohms. I have 1 ohm here. Okay, what's my total resistance? Total resistance is 1.5 ohms. They're in series, right? So I just add them together. What's my current?
2 amps.
2 amps. All right, 2 amps up here. 2 amps right here. And I can find my voltage. What's my internal resistance voltage? 1 volt. What's my load resistance voltage?
2 volts.
2 volts. And then finally, what's my power? So use one of your equations to find your power. So what's your power and the internal resistance? 2. And what's the unit? No. Watts. Okay. What's the power and the load resistance? 4. And then what's the total power? 6. Pretty straightforward. Not much to it. All I've added to it was the P. Fair enough? Yeah? Okay. There is one catch to this whole thing. So I need you to listen very closely. To calculate the maximum power given in the external circuit. So to find out what the maximum power is outside of the battery, out here, you simply change the amount of load resistance and make it equal the internal resistance. So to calculate the maximum power in the external circuit, in the load, you simply change that resistance and make it equivalent to the internal resistance. Just change it to 0.5. That will then give you the maximum power delivered in the load. Okay? If you look at page 454, they show you how that works. So they started with the same values in A that I had here. So your load power is 4 watts. Your internal power is 2 watts. Your total power is 6 watts. In circuit B, when the load resistance, this resistance here is smaller than the internal resistance, you notice that your power is 2.5 in the load, 12.5 in the internal resistance, and 15 total. So your load resistance went from 4 watts to 2.5 by making the resistance smaller than the actual internal resistance. Everybody follow what I'm saying there? So they changed this to 0.1, which is smaller than that, which took that down to 2.5 watts. But by making it equal in circuit C, what is the load resistance or the load power in circuit C? 4.5 watts. Exactly the same as this, and that's the maximum you can possibly have.
So what happens when you
Excuse me for the interruption. Do we have any students from grade 11 or 12 who require the retakes? Go to room 10 right now, and please bring your proof package with you. Again, students who require retakes from grades 11 and 12 only, please go to room 10 right now. Bring your proof packages with you. Thank you.
Ask your question.
So why for part D did they make it smaller, the R load smaller than the internal?
Just to show you that your power will go down. If this value is smaller than that, your power will go down.
Okay, so it doesn't
Okay.
actually find anything for
No.
us.
So to get the maximum power delivered to the load, you have to change it so that those two are equal values. Okay? That's all there is to it. There's 2 practice problems on page 456. And then there's 18 problems on page 457 and 458. I just want you to do the problems. That's gonna take you today and tomorrow to do. Okay? So you have to get at that now. I want a seating arrangement adjusted today. I don't want you sitting with somebody you have sat with before. Sit with somebody new. So if you're going to move, you guys are not all together in the same group you've been in. Find somebody else on this side of the room to switch up with. Grade 11 with a grade 12. You understand? Make your move and then get at it. Let's go.